Now let's look at a Venn diagram which has two sets A and B. Firstly, what would be the complement of U? The complement of the universal set would be all the elements that are not in the universal set. But because everything is in the universal set, U complement would be the empty set phi. Phi complement would be the set of elements that are not in the empty set, which would basically be all the elements that there are. So this would just be the set U. And of course we know that U complement should have been U. So if U complement is phi, phi complement must be U. Now let's take the complement of A union B and A intersection B, and let's see if we can derive a formula for them. And we want our formula to be in terms of A complement and B complement. So we want the complements to be applied to both A and B, and we want to express A union B complement in terms of A complement and B complement, and likewise the intersection of A and B and the complement of that in terms of A complement and B complement. A union B complement is the set of all elements that are neither in A nor in B. So if X is an arbitrary element of A union B complement, we can say that X does not belong to A because X lies outside of both A and B. So X lies in this particular region over here. This entire region outside of both the circles A and B would be the region that X comes from. So X does not belong to A, and X also does not belong to B. If X does not belong to A, then X must be an element of A complement. Likewise, if X does not belong to B, then X must be an element of B complement. So X must be an element of both A complement and B complement. This means that X must lie in the intersection of A complement and B complement. So A union B complement is A complement intersection B complement. So when we push the complement inside and apply it to A and B, we have to invert the sign of we have to invert this U sign, so the union becomes intersection. Now we also know that if we take the double complement of A union B, that would be like taking the complement of this right hand side. Since A union B complement is A complement intersection B complement, the complement of the left hand side would be the complement of the right hand side, and the complement of the left hand side, which would be the double complement of A union B, would just be A union B. This means that the right hand side should also ultimately become A union B. Now if we were to push the complement inside over here, A double complement would become A and B double complement would become B. So the effect of the complement on this intersection must be that it should invert this intersection and make it into union. So let me say this more formally. Let's say that C is the set A complement and D is the set B complement. The right hand side here is the set C intersection D complement. The left hand side here is A union B or A union B double complement. They're the same thing. So how would we express A union B in terms of C and D? If C is A complement, then A would be C complement, because if we take the complement of both sides, this double complement would cancel out. Likewise, if we take the complement of both sides here, this double complement would cancel out. So A can be expressed as C complement and B can be expressed as D complement. So the left hand side A union B can be expressed as C complement union D complement. Since the left hand side and the right hand side are the same, we can say that C intersection D complement is the same as C complement union D complement. Now because A and B were general sets, C and D are also general sets. So we can say that in general, if we take the complement of the intersection of two sets, then that would be the union of the complements. So it would be the union of the complements. So if you consider these two laws together, the effect of taking the complement is to invert this sign. If it's union, it's going to become intersection, and if it's intersection, it's going to become union, and the complement operation will get applied to both of these sets individually. These laws are known as deMorgans laws, after the mathematician found them. And we can quickly verify this using a simple example. So let's consider a situation where U is the set 1, 2, 3, 4, 5, 6, A is the set 2, 3, and B is the set 3, 4, 5. So what would be A union B complement? A union B complement would be the elements that neither belong to A nor to B. A union B would be the set 2, 3, 4 and 5. So everything outside of 2, 3, 4 and 5 would be in the complement of A union B. So that's 1 and 6. A complement intersection B complement would be, A complement would be everything except 2 and 3. So 1, 4, 5 and 6. And B complement would be everything outside of B. So everything outside of 3, 4 and 5. So 1, 2 and 6. And if we take the intersection of these two sets, we get 1 and 6. So you can see that A union B complement is the same as A complement intersection B complement. Likewise, we could take A intersection B complement. A intersection B is just the singleton set 3, and if we take the complement of that, it would be everything other than 3. 1, 2, 4, 5 and 6. A complement union B complement would be, we calculated A complement here as 1, 4, 5 and 6. Union B complement was 1, 2 and 6. So if we take the union of these two sets, we get 1, 2, 4, 5 and 6. So you can see that this set is equal to this set. So this was just an illustrative example to show that deMorgan's laws